Good morning. In a sec, I'm going to get to work, and I'm also going to join the IOA coffee time. But first, I wanted to share something quickly. Because I solved the puzzle last night or this morning. I've been wondering for a while. The imperial coronation of Charlemagne. I've been wondering about this. No, I've been wondering for a while. I just want the actual paper. Why UK schools aren't yet closing, and is this the one I want? Yes, looks like it. Yeah. And I think I've worked it out. Like, this is conjecture, but yeah, take it with a grain of salt. But I think the rationale can actually be seen on these graphs. So this is the number of beds occupied, which is kind of the biggest priority right now, that we don't have overoccupation in hospitals. Hey, Lewis. And one of the really big fears is that that number might exceed, the number of people who need hospital beds might exceed the number of hospital beds by orders of magnitude. Like, you can, this red line right at the bottom of here at 8 is nothing compared to curves that peak at hundreds. And the blue, yellow and green show 3 different cases, 3 different tactics that we could be using. The blue is do nothing, which we're not doing, we shouldn't do, it's a bad idea. The yellow is do basically everything but school and university closure. And at this point, really just school closure, like universities are basically closed. Not all of them, but lots of them. And then the green is with school and university closure. And the yellow is the path we're currently on. And looking at this, I can see, if I had to make this decision and I was presented with this graph, I can see why I would choose this course of action. The yellow is potentially overwhelming UK healthcare by a factor of about 2, which is a huge problem and will cause a lot of harm, but it's a lot less than a factor of 10 or a factor of 30-ish, which is what we'd be looking at with doing nothing. But this means also that a lot of people will get the disease, and this is what people are talking about when they talk about herd immunity. And herd immunity as a phrase, I think, struck a lot of people badly. It's not a completely foolish tactic, but it is also potentially quite harmful. But I think here we see herd immunity as a thing that we can more easily rationalise. So this is the same graph, A and B. The only difference is zooming in on this very low level region. And the current tactic of keeping schools open, I think it's quite likely the UK's intention to stay as close to this line as they can, because flu spreads best in winter, and if we just cut down the spread now and then don't change our behaviour in winter, the flu spread of if you do school and university closure and then you stop it in September when the number of cases has gone down to none, is about the same as doing nothing now. It's just putting the problem off. And this is very conditional on what tactic you do. For example, if you keep doing some kind of social distancing measures, we can put it off further. But it's not foolish to want to have as many people exposed to this as the system can cope with. Dependent on one or two really crucial facts. One of them is, are you any less likely to get the disease if you've already had it? The current assumption is that you probably are, but that's not known for certain. And also, there's always the question of when might a vaccine arrive, which is kind of unguessable. A vaccine just possibly could arrive tomorrow, although I think it's incredibly unlikely. It could arrive in 3 months, it could arrive in 9 months, it could arrive in 2 years, and it could never arrive at all. So this yellow path that we seem to be taking is one which has a lot of cost. Any time you spend above this line, and you even see like their modelling, I wonder if this is school holidays or something, has a kind of peak that then resides and then goes back. I think their tactic has been for a while to stay at this peak. I think that's what they mean by herd immunity. So this is just my take, but I found it hard to understand why schools were remaining open. And looking at this, I can see certainly not necessarily correct, but I can at least make sense of the thought processes going on in people's heads. And that to me is important. That makes me feel more grounded in a world where things are happening for good reasons. I'm going to jump into IOA coffee time. Oh, there's no one in IOA coffee time. I'm going to jump in anyway and just keep talking to myself. Someone might turn up. They're all in doing the crossword place, but I don't fancy much doing the crossword. This is a daily thing. The grad students in our department do the Guardian cryptic crossword, and over a year I've become semi-able to do it, but I still find it confusing and hard. I've been well, thank you. Fatigued. I think that a lot of that fatigue is just uncertainty. It doesn't seem like if we did pick up the virus from our 1 degree of separation, we seem to be going through mild cases. There's little evidence that we have. Like we haven't been coughing very much. So just the normal weird everyone's at home. I'm trying to work out what they're doing with that. I want another window. Separate window. Overleaf. How come, are you at home today? Or are you just in a free period? Windows 10 has this like ambitious thing where, okay, yeah, that is the edge of the window now. Where it says it's going to make it the edge of the window and then it doesn't. I had an idea yesterday that I wanted to do one more of these. Oops. That's cool. It keeps my session open. I'm seeing a lot of teachers for relatively good reasons, like everyone for themselves deciding to stay home. If you ever want to see what the inner lives of your teachers and professors looks like, go and find them on Twitter. It is both Some teachers will be like, oh, I can't believe you're actually pointing people towards knowing our secrets. Although it's nice, it humanises people. Don't really need the file tree. Definitely don't need this being so huge. Maybe don't need it at all. Gonna try and keep everything relatively readable. I have errors. Oh, because I deleted the plots folder. Well, it'll be fine. How do I reply to a thing? So yesterday I did most of the groundwork that I'm going to need to do for normalising this sensibly. Can I? Yeah, make it dark theme. So I was sort of hoping that some of these might be normally distributed, and they really aren't. Love making sure always that the galaxy looks right. No, that's a terrible galaxy. It's like 5 galaxies. Because we are now looking at halos. So that has some sub halos, but it's pretty sensible. Actually, there's still furring out. So this is something that makes looking at these systems really hard. All the substructure can completely dominate your analysis of them. Oh, talk me through where you are. I saw you posted in Discord a couple of days ago that you were having to learn the maths and physics of it. Oh, that's terrible. It is a lot of what I spend all my time thinking about, so hopefully I can help. There we go. That is finally a nice behaved one. (2D Suvat). Interesting. So Suvat won't I don't think it will help you. I wish we didn't teach Surat. Surat is in the very particular case that there's constant acceleration, and those equations don't work when there isn't constant acceleration. Let me show you how I would go about simulating this. I would use leapfrog integration, where the really basic thing you're doing, if we ignore some of the subscripts on these for the moment, is you find the acceleration at a point in time, you update the velocity by that acceleration, and then you update the position by that velocity. And then you do this over and over again. I like doing it in this form, which is just kind of a rearrangement of the steps, the kick, drift, kick form, because then you actually have, like, the reason it's called leapfrog is that you work out the velocity at one point, position at the next point, velocity at the next point, position at the next point. You're kind of jumping over, so this is why we've got half time steps. So the ith time step, you want to go the ith time step, the ith plus a half time step, the ith plus 1th time step. I honestly find that confusing, so this form I like better, which you do go through the half time step, but you get out of it. It tells you how to get from vi to vi plus 1 and xi to xi plus 1. Does that make sense? It's one thing that it's not easy setting up a leapfrog integrator. Well, it kind of is, but I tend to get my students to do it whenever a new student starts working with me, because I think it, one, they often use it, and two, it's a good entry point to a lot of the tools they're going to use, like doing it in a nice sensible way where you're keeping track of the properties of every particle well, and it's relatively efficient. Yeah, it's just a nice task. So I think I want to find the, I'm going to change some of these colour maps as well. That's what's important. There we go. We've got backgrounds on. Oh well, that's so important. And I'm going to stick some music on, just to have. Oh, I just realised that I had no sound on, so. here. So I like finding the peak by finding the fastest change in the CDF. And the difficulty for that is you have to know so let me give an example of what that means. Oops. Are they called R's? Yes, they are. So this is what our histogram looks like. Let's normalise it so it's kind of easier to see things. Let's have more bins, 'cause why not? There's a lot of data here. And I want to compare the sorted R's to there we go. Oh, feel free to keep checking in. Like, it's really hard to get the knowledge you need and know where to look for it, but occasionally it's when people can be most productive when they actually come across a place where just the knowledge that they need is being freely given. And yeah, it's definitely being freely given on this place. Any knowledge, information that people want, they're welcome to it. These halos are so badly behaved that I'm going to go back to using sub-halos. Do I just want a little bit lower mass? What? That's quite broken. There's a single particle all the way over there. That one seems fine. All of these, though, we're not even really resolving. We're just about resolving the peak, but only just. Well, this one will do for now. It's one of the things that I really hope might come out of me and encouraging other scientists to kind of live stream. Having really easy access to kind of ask an astronomer something. So, the peak of this should come at the steepest gradient of, because effectively what's in blue is the cumulative distribution function. Do the halos really have this hard edge? I kind of want to look into this, because if they do, there's our splashback radius. How can I have a look at that? That feels important as like a first step. So if I switch to a smaller simulation, it's going to be a good idea. This is just a low resolution one. And TNG50 isn't out yet. Okay, let's go for the lowest resolution because it will just be easier to work with. So look at, oh, God, that is very low resolution. Let's go up the mass a little bit. Yeah, no, that's too little. Let's try TNG2. That's still pretty awful. Let's have a look at the histogram of masses. Hey, viewer number 2, where are you joining us from? Let's put it in, whoop, there's another one. There is another conversion factor of like 0.7, but I'm just going to completely ignore that. So there are some above. This is kind of the limit. These are the most massive things in the simulation. Let's see what that top level really looks like. So there's maybe tens. Yeah, above. Oh, no, I mean 100. Let's look in that range. Sometimes we might get we don't want the absolute biggest one, so let's keep it under 1,000. See if these are well enough resolved to look at. Okay. That looks like it might be a reasonable halo. Yeah. And let's just see if they're any good in TNG3. So each time, what are we going down by? We're going down by a factor of about 8 in resolution. Yeah, I can work with this. So, now the question is, how do I actually get um, that halo? So I could just download a snapshot, but those are expensive. Why are some snapshots 30 gigs and some are 10 gigs? That doesn't make any sense. But I want to see if I can do this without on the API. So I want to get the particle data some small distance away from just a pointed space. So I think I can see the merger tree for any halo if I do this. Oops. Nope, it's forbidden. Oh, maybe it is just this one. Or maybe I can generate it somehow, but I haven't yet. So this is one where the merger does cut off star formation. I just had a thought, which I'm going to share, even if it makes absolutely no sense. So for a while, a lot of the picture of what happens in the evolution of galaxies is galaxies undergo what we call mergers, where two galaxies crash into each other, and that's the moment where a lot of their behaviour changes. And I completely agree with that, and I think simulations show that really clearly. Mergers are very important in the life of a galaxy. But I think sometimes we're slightly off the money with why the merger is so important. And sometimes I think it is the entire course, but sometimes I think it's also actually a symptom of what's happening, which is that whole regions of the cosmological density field are running out of gas. Like if you're feeding off a nice well of gas, if you're a galaxy and you're pulling gas in from somewhere, you actually tend to be pulling it in from one direction because that's the way gravitational collapse happens. You have a 3D thing, it collapses down into a 2D thing, that collapses down into a 1D thing, and then that collapses down into a zero-dimensional object. And that's what galaxies are. They're things that have gone through all those stages of collapse. But they still have, like, that collapse takes time, and so though a lot of gas has come down and formed the galaxy in a 1D object, the tails still remain. And galaxies need to be feeding from gas their whole lifetime. Otherwise they just stop making stars and kind of become pretty boring. And we often see mergers as turning off star formation because of the energy injection of these two things coming together. And whilst I think that's almost certainly true, I think the thing that's harder to see, and maybe similarly or even more effective, is the turning off of the gas accretion. That's kind of hidden under this big violent event, that's this much more subtle event that's linked. Because if you think about it, if you've got this kind of things have tended to collapse down to small spaces with the kind of last bit of gas coming in, as two galaxies come close to each other, it's almost like imagine someone cycling with a scarf trailing off them. That's what that gas is. It's the scarf trailing off them, and as you, that means that the moment that you actually eat the galaxy isn't necessarily the moment where everything changes because you've eaten the galaxy. It's because the galaxy is the thing at the end of the scarf, and that means that if you're getting to eating the galaxy, you've run out of scarf. It's clear as hell, wasn't it? Oh well. Let's keep on exploring this. Okay, so we really can load all of the dark matter. That's great. That's exactly what we want. And I just want the coordinates. So this will probably take a little while to run. Let's do it here, and it's done. It shouldn't break, given that it could do gases, it shouldn't break the notebook. Because gases are give or take, there should be the same number of gas particles as other things. Yep, that loaded away. Oh no, I got rid of my nice halo that I liked, and now I have. Oh, that looks okay. No. No, it's okay, but no. I really liked my first one. This one's actually pretty great, apart from the fact that it's got one particle all the way out here, so I'm just going to ignore it. That looks hopeful. Yeah, alright. One of my small contributions to the illustrious collaboration was, I think, pointing out that this tree was quite broken. I think it was quite broken. I hope it was. Otherwise I was just actually having bugs in my own code and blaming someone else for them. But who would do a thing like that? Okay, so we have a nice galaxy that we like. We have its midpoint. This will probably take a little while to do. But I'm gonna try and plot the whole dark matter web. it called? Alt DM. I don't think anyone's coming in this chat. All busy crosswording. I just want the coordinates. Also, that's the only data I have. Don't care about x dot mid. Actually, I don't care about that either. Just want all x's. So let's get rid of the log scaling, because otherwise I think we won't see anything. We probably still won't see anything, and it'll take ages to do it. So this is clever. Using my time. What's wrong with that? Oh, because it's only one, it loads that way, which sort of sucks. It's a cool way to have it not do a deep copy. Yeah, as expected, this is slow. There we go, it looks like some smudges. Kind of looks like mould, doesn't it? Given that I'm actually just going to quickly reply to an email, let's... No, that's not what I wanted. That's what it is. spell that word. I regret running this again now. It's taken too long. I'm impatient. Seems to be taking longer than before. It surprised me if logging the bins did that. While it's running, this is something that I advise of anyone who's coding, to do their best to not have things that take a long time to run, because when something takes a long time to run, it's hard to keep concentration, it's hard to keep working on the thing you're working on, and it's really easy to slip into doing exactly what I'm doing now, which is checking all your social media and you know what? This is. I'm going to just quickly publish an essay. Oh. It's been a while since I published an essay. Something I wrote this morning. Very short. Italicize that. Grab a nice Google image, Google picture. God, it's been too long since I published an essay. Why is the image not showing up? Okay, there we go. It's still going. I think it's crashed. We don't actually need this, so what I do want to see is rounds ago. Keep forgetting this. Just on 0. So I'm just going to go for square. It's relatively easy. No, let's go for a sphere. It's no harder. In fact, let's do it properly. So this is the distance from all the particles to the centre of the particular galaxy we're thinking about. Now that should be a tiny fraction of all of the particles, so I should be able to plot them in finite time. DM is not defined. Oh, did the kernel actually crash? Give it a little moment. Okay. There we go. That is a little slice of the box. This is not the best behaved galaxy, so let's keep looking for another good one. This cell is doing nothing. That's going to be 2 at least. Yeah, look, 2 almost equal mass in a halo. Lovely. That's going to be okay with a few small ones in it. I want to go for one that's really dominated by its central object. That was good. Yep, that was great. Let's put the number of bins down on this. They are so low particle numbers. I'm gonna go a little bit higher mass. This will almost certainly lead to more that have multiple objects in them, but it doesn't hugely matter right now. Yeah, look at that. Few little ones, but mostly one major thing. Again. A few little things, hopefully not too major. Just make things actually circular. It's okay, I'm still not too happy with it. That looks good. Yep, close enough. Perfect. So, it's got that little hump down there, but clear center. Box size 10 is obviously too big. Box size 100 is probably going to be too small. That's okay. We get catching the same shape. Let's stop stretching everything so much. Obviously, I did that on the wrong plot, but capital. Pins? No, what is it? I can't remember. Grid size. We can go a bit above that. Then we've got that overlapping problem. How do I deal with that? So I can just turn down line widths apparently. Can I just make them 0? So that's the state we have. Let's make this a bit bigger figure. No? Yeah. Okay, that's looking nice. I could do this. Almost no difference, but no, I like it this way. So let's just make these truly comparable images. What have we changed here? Grid size and line widths. Cool, so we can see that we're like a factor of 2 more zoomed out. So now we can do exactly the same graph. Let's get rid of the set aspect equal, just making the y-axis too small. Loads of plt.shows, but that's fine. So I want dists and I want in box. It's taking a long one because dists is actually quite expensive. Finding dists is quite expensive. Let's have this on the same plot. And I want the true numbers because it should be the same distribution, but I want some transparency so I can see everything. Pasted that in the wrong place. 0 to 3. And 64 bins. Will do fine. Interesting. Let's look at small galaxies. This is number 404. No, it's not. It's number 10, 5, 6, 7. Is it the same cell twice? No, it's doing it. So it's a well-behaved one. So what we're kind of seeing is that actually at some point it starts to tend to the background number. And that's not too shocking because our sphere is getting bigger and bigger. Need to think about this a bit. Oh, it's past 12. I should do my primer video. Be back in a sec. I'm going to do my book club for the day, and you know what? I think I'm coming to peace with my at the moment quite short days. Just trying hard to not feel bad about it, basically. Oh, YouTube has recommended that I might want to watch my own stream. Yeah, sure. Oh, this is what it looks like on YouTube. Interesting. And what gets recommended attached to my videos? Fine things. Meta. So it's turning music off a little bit late, but no one's gonna mind. So where are we? We're at mutations in the first replicators.
In the last video, we saw that when
I'm glad that he's going to do a recap. It means that I don't have to. For anyone seeing this for the first time, I'm doing a daily reading of a book that happens to be a YouTube series on evolution and population biology, because it's cool, it's interesting, and it's relevant right now. And I'm doing it roughly at midday, and it's if you want to start getting your head around the mathematics of what's going on in the world due to COVID-19, this is a good place to start.
when a creature's replication chance is higher than its death chance, its numbers can grow exponentially. But we were left with a mystery. Since complex organisms can't form without replication, it doesn't matter how good they are at replicating if there aren't any around to replicate. So how do they get their start? So far, each time one of our creatures has replicated, it's done a perfect job. They make an exact copy every time. In the real world, though, nobody's perfect. Sometimes a mistake during replication causes a new kind of creature to appear. We'll call these mistakes mutations. Whatever's different about that kind of creature, color in this case, will likely have some effect on the statistics for that creature. The blue kind of creature has a spontaneous birth chance of 1, which means that every time step in the simulation, one of them will appear. And each time step, each blue creature has a 10% chance of dying and a 5% chance of replicating. So how would a green creature be different? Well, to be totally honest, we're just making things up right now. We're not looking at actual creatures in an actual environment, so it's totally up to us to decide what this change might do. And then we'll use our equations and simulations to see how things play out. Eventually, we will tie this to the real physical world. Stay tuned. But making stuff up and looking at the
Love this deep
helps us
zoom.
understand the deep mathematical truths that apply to all replicators. Anyway,
I think you're zooming there to almost apologise for going a little bit philosophical. Obviously, you don't need to apologise about that from me. But the deep mathematical truths, I think, is a good way of putting this. There are deep mathematical truths underlying all these behaviours, and I keep on saying this because I keep on being worried that there was a phrase I was introduced to recently by the generally excellent Citations Needed. I think they used the public school sociopath. And one, I was like, oh my god, what if that's me? And two, I think more generally, there is a sort of cold and sometimes callous way of talking about and using and comparing mathematical reasoning and things from data science, and it's not actually, and it's for people who don't understand the language, it's both quite exclusionary and completely impossible to argue with. Like, if you try and have an argument with a mathematician, they will say, because they don't know how else really to have it, there's no such thing as a mathematician, but they might be like, well, yeah, it's a nice set of thoughts, but can you show me a model of it? Can you show me an equation of it? Can you map it to something rigorous? Because it's really hard to understand things outside of that scope, mathematics is this incredibly exacting language, and it does reveal deep truths. But it reveals deep truths comes on its own terms. Like, you don't get a free lunch in mathematics. You have to do pages and pages of this stuff. But if you do them, you can maybe, sometimes, 1 in 5 times, find the structure of galaxies or find
Hey, let's pick stats
the
that
evolution
might
of
be different from the blue time. After
molecules.
all, it comes from a mistake in a process that normally works.
bacteria, whatever
So
we're
let's keep the
evolving.
same death and replication chances for creature, but get rid of that non-replication birth rate. So the blue
So this is kind of taking something that was just popping out from nowhere. So you can imagine, imagine a really simple molecule that's just about able of replicating. We'll see some examples in a sec, and in fact, the one that's really relevant here is RNA, which is exactly the thing that COVID is using to replicate. But we're going from something that pops out of nowhere, has a birth chance that it can just be born out of nowhere, to something which doesn't pop out of nowhere.
The blue creatures will be essentially the same when they're alive, but for some reason, green blob skin doesn't form unless it comes from replication. Oh, and we should also keep track of the chance of the mutation. Let's say it's 10%. This means that whenever a blue creature replicates, there's a 10% chance that a green creature will reproduce instead of a blue one. Alright, let's look at a simulation. After watching for a while, we can see that the green ones are having a hard time compared to the blue ones. No offense to the green creatures, but this wasn't a very good mutation.
So basically,
It's easy to think of evolution as a forward march to making better and better organisms, but it's actually a bumbling mess that just gets licked sometimes.
oh yeah, this is like, I think one of the hardest points to grasp, given the way that evolution is often talked about. Most evolution is bad. Most mutations are deleterious. There's a lovely phrase for this, which is the nearly neutral theory of evolution, where you basically say, like, well, it's really hard to have a mutation that gives you a huge advantage, and even if your mutation is kind of advantageous, the random chance of life means that it probably won't get a chance to show itself off, which both means that good mutations can die out and bad mutations can succeed. But there is one kind of mutation. It's really hard to get a good mutation, but it's very possible to get a bad mutation. It would be hard, like, we're a delicate thing that small changes to us being any organism, aren't going to change very much our function, but could break our function. So yeah, evolution is not just random, it certainly isn't, it doesn't push forward. The only thing that pushes forward about it is if you look at it over long time scales, you have enough tests, basically, enough statistical attempts that any small advantage eventually has a chance to win out.
We'll have to look at some good mutations in a moment, but first let's add these mutations to our equations from the last video. Just like in the last video, the total expected change will be equal to the non-replication birth rate plus a term that depends on the current number of creatures. In the last video, this was the replication chance per creature minus the death chance per creature times the total number of creatures. Mutation affects what happens when a creature replicates, so to add mutations into this model, we should do something to this replication piece. But what exactly? To think about this, say 10 blue creatures replicate at a certain time. Without mutations, all 10 of the new creatures will contribute to the number of blue creatures at the next time step. But since blue has a 10% mutation chance, on average we'd expect one of those creatures would actually come out green, so only 9 of the 10 new creatures would be added to blue. We can account for this loss by multiplying R by 1 minus M. With a 10% mutation chance, 90% of blue replications will convert into blue creatures. Alright, what about the equations for green creatures?
For people who don't feel very comfortable with mathematics, this is probably getting to quite a lot of abstract things. I think algebra is a whole different way of thinking about mathematics, not like we're dealing with this number and it does this, but we're dealing with something that eventually will put in a number in that space. And this might be getting to quite a lot of symbols. Maybe not. Maybe I'm being. It's hard to. It's always hard to see what the difficulty is in something that you yourself feel comfortable with. But if this is seeming like a lot of symbols, I recommend going back and just carefully going through when each of them is introduced. To go back through the old videos, go back through either my book club about it or just the videos themselves, and really carefully understand each term. And this is something that I think I quite naturally picked up some point during my maths education, but I wish someone had told me, and no one ever told me. Never let a step pass you by. Which is a hard thing to say because it means that if there's some difficult step, you have to go through with it. If you have a good instructor, if you have a good guide, they'll never put a step in front of you that isn't important, because sometimes you work really hard to understand a step and then you're like, oh, this didn't matter at all, this was just fluff. But don't be ashamed that it takes time to get things. Don't be ashamed, basically. Shame is this awful emotion that some old-fashioned teaching structures that still abound that use shame as a teaching tool, and it's a bad one. It works, but there are better ones. Go through and try and get every single step. And if you don't get it, go through it again. Because maths is an inductive process, and to make the next step, you'll probably need the last one. Just take your time. Like, if it helps, and I know I have my own strange mind, but if it helps, I didn't understand anything first time through in school, but what I did tend to do, or in university, or now as a working scientist, what I did tend to do is kind of in my own time, which would sometimes just be sitting in the lesson, go off in my own world and induct my way through it. And so for me, maths and education generally really took a corner when at some point during A-level, so age like late teens, I got given the tools to induct from scratch, and I sort of just went through working out all the maths there was. I would encourage myself always to go back to the most basic principles, work my way up, and although that's a slightly long-winded route if you want to learn any one thing, there's a lot of shared structure. So if you really work through in your head, like where trigonometric terms are coming from, you've done most of the work for really working out differential geometry. If you really work through in your head how integration is working, you've also set yourself up for looking at differential equations. And it's slow, and it takes time, and everyone is always a bit time starved, but there's maybe more time now than most have had before. And this isn't a bad time to start learning some of these things, if you want to. No judgment if you don't. Maths is a strange hobby, but a rewarding one.
Again, we'll start with the equation from last video, but before we do anything else, notice how we're using the same symbols in both equations. The equations are actually talking about different kinds of creatures though, so let's add some labels to keep them straight. Okay.
If you're watching me latecking, this is exactly why I spend so long finessing all the little details, just to make sure that there's no symbol being repeated between two things. And this happens all the time. Sometimes I'll send a paper to a collaborator and they'll be like, I didn't understand for a while, but then I worked out that you're using 4 different things, the same symbol for 4 different things, and you just lose track of these things. I have some papers published which use the same symbol for multiple things, and just little things like that make stuff harder, but I think this is relatively clear. This is talking about creature 1, this is talking about creature 2. I sort of wish that he'd subscripted the deltas as well.
But we'll add add another term to the end to account for the new creatures that appear due to the blue creatures mutating.
So now's not a bad time to pause and see if you can actually work out what this number should be. And I'm going to steal his thunder and work it out myself. So how many blue creatures are appearing because of mutation? Well, it's exactly the same number as how many green creatures are appearing because of mutation? It's exactly the same number as the number of blue creatures disappearing because of mutation, which is N1, R1, the number of blue creatures that are appearing because of reproduction, M1, the number of blue creatures that, while reproducing, are mutating into green creatures.
What should this term be? Well, if we multiply out the blue equation to get rid of all the parentheses, we can see this term here, which stands for the blue creatures that would have come from replication, but were instead born green due to mutation. These are the same creatures being added to Green's numbers, so we can use the exact same expression except added.
So there's a quite fundamental link to these equations, and as we go forward, we'll see more and more links between these equations, because I hope it's clear at this point how these equations are describing a real population. A slightly idealised one, which has these magic birth chances and magic reproduction chances. As those links get more complicated, we'll move from things that are solvable with a pencil and paper to things that can have many different solutions and even move between solutions. And just like with any system, that transition will happen as things get more and more complex, more and more interwoven. And for anyone wondering, why does everyone, even the most studied of epidemiologists and mathematical biologists, why is there so much uncertainty about coronavirus? And this is a lot of why, because there's many interlocking effects. There's also, depending on your viewpoint, a lot of certainty about coronavirus. There's a lot that we know kind of exactly how it should be behaving given a set of assumptions.
This might not seem like it, but this is a big moment. The green creatures can't form on their own, but this mutation term shows how the green creatures get above zero. Their existence depends on replication alone, but in a way they've hacked the system by depending on the replication of a different kind of creature. From their perspective, it's basically the same as being able to form without replication. So even though there weren't too many green creatures, this is a moment to remember. Alright, so that's one possible mistake a blue creature can make while replicating, but as you may know from being a human, there are many, many possible mistakes you could make. So let's add a few more, which will lead us to new kind of creatures. First, let's say blue can also mutate into this red kind, also with a 10% chance each replication.
It's a small thing. I really do like these videos, but he's about to introduce 2 new creatures, and for exactly those same reasons. So it's going to make it a little bit harder to picture everything that's going on, because you're kind of looking at the interplay of all these different creatures. At the moment, apart from the fact that the birth rate of all these creatures depend on the blue creatures, they don't really interdepend. They're not competing over anything. But still, it's going to put quite a lot of complexity in pretty quickly.
Both of these mutation chances belong to the blue kind of creature, so they should keep the label 1, but since there are 2 of them, we should add another label to tell them apart somehow. The first mutation chance leads to green creatures, so we can add a 2 to keep track of that fact. And this second mutation leads to the red kind of creature, which we can label with the number 3.
Small thing, but blue is actually getting less fit every time we add one of these mutations. If both of these percentages were 5%, it wouldn't, but it's getting more and more chance to mutate into something else. Equally, just quickly worth thinking through in your head, which of these 2 is now the better creature? Which one will survive better, will reproduce better?
With that sorted out, this new red kind can only come from replication, just like the green kind. It can't form on its own. But it has a difference. Its death chance is lower than that of a green creature, or a blue creature. For some reason, red blob skin is stronger than green or blue blob skin, or something like that. Again, we're imagining a situation and seeing what our model predicts about that kind of situation. explore the deep mathematical truths behind replicating. Next, this orange kind. The blue creatures aren't the only ones that make mistakes. The orange ones come from red ones, with a chance of, say, 5%. The label 3, 4 here.
Also, we've just got so many numbers in the mix here that I think the general behaviours are still quite clear. And I like this way of showing it, but it would be hard, and in some ways this is a good example of why population biology is from something that is hard. It'd be hard to make a really clear prediction of exactly what's going to happen based on these numbers. Some general predictions you probably could make. Blues are going to keep being born no matter what, so there'll always be some blues, even if they die out, like a few of them will pop back in. Some fraction of those will turn to greens, but greens will do less well than reds, and some fraction of reds will turn into oranges, and oranges are going to do great. Oranges, although they're not born out of nothing, have a higher replication rate than their death rate, so their population should just explode.
That keeps track of the fact that it's about creature type 3, which is red.
Also, worth pointing out that because greens have a higher death rate than their replication rate, they should die out. They might stick around for a while, like that is again a random process, but they should die out. Reds should have a stable-ish population, although their actual replication rate is effectively a little bit lower because some fraction of them turn into oranges. But at the same time, they're being topped up by blues the whole time. And it's even possible that the topping up by blues keep the populations of greens steady, and quickly we're getting to the point where it's hard to make any clear predictions. It's actually workable out if these populations will keep each other steady or help each other grow, but it's a few steps which you can do in your own time if you want.
10% instead of 5%. Continuing with our amendments, orange blob skin is also strong with a low death chance, but it's also easier to make more of it once it exists, or something. If you saw the last video, you might notice that the replication chance being higher than the death chance means this creature type has a shot at growing exponentially. Alright, let's run a simulation starting with no creatures. As expected, the blue creatures are strong coming out of the gate. Like before, we have green here and there. Okay, there's some red, so now we have a chance to see some orange.
Okay, our first orange.
Oranges, we can really see that high.
And orange is just so much better at being that you can already see it's just going to explode in population.
Blue looks like it's around its equilibrium number. The orange is growing exponentially, so.
Remember that blue doesn't actually care how many other things are on, so it should stay at roughly this equilibrium the whole time. Reds are. They have that potentially stable population. They're not going to zero like greens, but they're not doing great.
Looking back to this tree we started building, two of these kinds of creatures are extra special. The orange kind is the first type that grows exponentially. Now that it's around, there's lots and lots of replication happening, and that means lots more chances for mistakes. And that means lots of new kinds of creatures have a chance to develop.
So this is, I think, a really important point that I just wanted to make clearly. The thing that you most want when evolving isn't being the fittest, it's being sufficiently fit to survive and making a lot of variation. But one way to make variation is having a large population, because you've effectively just got more chances. So there is an inherent bonus in being very fit. And it's a bonus that there's just a lot of you, but fitness now does not translate to fitness in the future. Like, fitness is a short-term requirement on these creatures that they must not die out, but it's not the long-term distinguisher of success. And I think that's quite different from the way that evolution is often talked about. Particularly, like, phrases like survival of the fittest are, you'd struggle to find a biology classroom where someone says this without a caveat, but they are still in our like general talk about these things, and they're really misleading because yes, the fittest, survival of the fit enough would be a much better way of putting it, and then success of the most varied.
Actually leading to some pretty complex creatures. And this blue kind is the first predator.
So it also shows how, even though the evolutionary path can be branching off in different directions, there can be a really common route. Like, I think we'll talk more about this as this series goes on. I really encourage people to stop thinking about evolution in terms of like the branching trees of Darwin's sketches. They're not wrong, but, well, they're a bit wrong. And more as flows of a river branching and occasionally recombining, with different amounts, different volumes of water going off in different directions at different rates.
It's simple enough to form without replication
In a high number of dimensions.
in the right environment, but it's also complex enough to make more of itself. And even though there's never a huge number of them, it's the seed that everything else comes from. So if we were imagining the situation, why did we bother with the green and the red creature? Wouldn't it be more convenient to just have a blue creature mutate directly into an orange creature? Well, maybe, but that feels a little bit too convenient, don't you think? The real power of this way of looking at replicators comes from the fact that even a messy system full of bad mutations can lead to some exponentially growing replicators. In fact, the reality of how life started is probably much more complex than what we built here. But no matter how messy things get, as long as there's a first replicator and it makes mistakes, odds are good that we'll eventually stumble onto a creature whose replication chance is higher than its death chance. And then the tree of life begins to sprout. We're still working out the details of how this played out in the real world, but we do have a leading candidate for the first replicator. It's a molecule called RNA. The basic story with RNA is that it's simple enough to form without having to come from replication, and yet it replicates, creating more of itself.
Like, it is simple enough to form without having to come from replication, but look at that thing. Imagine trying to design it. This is, in the early days of evolution being posited as a theory, this is one of the things that people found most difficult to get their head around. You have to make something really pretty complex to be able to self-replicate. And so it comes down to a question of timescales, like how often would you expect this thing to appear at random in nature? Of course, it isn't quite at random, but if this is your fundamental building block of a self-replicating creature, it's not that easy to make. And maybe I'll show you quickly. Game of Life was early in... No. Do I mean... Here we go. Conway's Game of Life. Was an early way of kind of thinking about wow, this is deep in a terminology I don't know. Thinking about these kind of replication structures, and it's a set of rules about a grid where, for example, if I don't remember the exact rules, in fact this says it's from High Life, which may not be the most basic one. A cell is born if it has 3 or 6 neighbours, and survives if it has 2 or 3 neighbours. So it may be designed specifically so it can form replicators. You can see that one shape keeps on replicating itself. In fact, it replicates itself in a kind of pattern. This isn't so complex, but then we have a really simple rule system here, much more simple than the rules of chemical evolution. Such that you could imagine actually if you just put in some random noise onto this grid, it might well form this just by chance as it evolved, and then that thing might be stable. But that thing also might be, that random noise washing about might also disrupt it. In fact, can we have, let's see what I find typing in this. Can I actually just play it somewhere? If not, oh, hello. So this, I don't know why it's moving upwards. Oh, because the whole thing is moving upwards. It's actually tracing out a path. So there's a lot of what are often called gliders in the Game of Life, things that just move by these rules constantly. You can see this kind of complex spaceship, as they call it, moving up in time. if I get rid of this, if I clear the grid, zoom out a little bit there, more. That's not doing very much. Graph, that's not doing very much. Pattern. New pattern. Show me the grid. Okay, so yeah, I can just put some dots down. I don't know if I can change the rules on here, but let's just let this run. So a lot of these, Conway's Game of Life is one rule set and is not the most sustainable. I forget exactly what a glider looks like. It might look like this. No, but it makes a stable pattern. Although that's, and you can see these are making stable patterns that keep themselves going. And eventually we get to a state that is just kind of a bit stuck. And then let's see. Oh, that's nice. Okay, so yeah, this is a glider. No? Oh yeah, I can just click start and it will go. This is a shape that just moves its way across the page by these rules. Do you know, if you just sent me this, where I can find a place where we can do high life rules rather than game of life rules? What happens to this? Oh, it kind of grows outwards, and then it's not far off a replicator. Like, you can see sort of common shapes made here. In fact, it has gone back to a state that it was originally in. It is in a loop. It hasn't gone back to the full initial state, but I'm pretty sure that like almost filled in with a line in the middle was there. Anyway, we should finish the video because. Oh yeah, what are the rules exactly? Cells with one or no neighbours die. Cells with 4 or more neighbours die, as if by population. Cells with 2 or 3 neighbours survive. So cells like to have a medium number of neighbours in the game of life. High life, with these really particular rules, seems quite different, but it also. Just gonna have one more go at finding it. Maybe? One sad thing about anything made by academics is. Oh. Wait, you think if I replicate this, it will work in Conway's Game of Life? I don't think that's true, but I am also wrong all the time. How can I reset this? No? Settings. Pattern. New pattern. Show me the grid, and let's try drawing this thing. 1, 2, 3, 2, 3, 1, 1, 2, 3, 1, 2, 3. So. You might be. Wait, no, it needs to make a copy of what we originally had to be a replicator. It's a kind of exploded copy of what we originally had, but yeah, and then we get to this. So it doesn't. It's not a replicator in these tools. Is this the rules? Unless we can change the rules. rotate. Oh, change rule. That's not changing the rule, that's just changing. Is this truly randomizing the rule? Oh god, oh god, oh god, oh god. This is just a grower. That I expect will happen most times when you randomize. Oh, this grows. Oh, lovely. Why does that grow as an octagon? I'm going to keep on randomizing. This grows as something that looks very fractal. This grows as something that looks basically random. This dies and then stays there. So where is this rule being set? I don't understand. I could play with this for hours, and I recommend for anyone who wants to play with it for hours. Conwaylife.com is where I just found this. Oh, this is a slow grower. Wait, I want to keep on randomizing because this is fascinating. Haha. Wonder if that's the original. Let's just stop it because eventually we'll get way too. Yeah, that's the original size of the box, the central thing, and you can see that it's basically just growing out here. God, this is hard to look at. But that some of the initial perturbations here have propagated their way up. The game of life is one of those things that has the lessons of how it works. I think this is aliasing. I think these grids are all the same. Oh no, they're not. Look, there's some of them are offset. I guess because they're interactions between different bits of this, and then it's taking time for those interactions to propagate outwards. You could explore these things for hundreds of hours, and you know what? I recommend it. Call it a hobby, play around with them, and you might just find out some much deeper mathematical truth. Some of it will be known, and some of it probably will not. The fraction of it that is both not known and immediately useful is going to be small, but honestly, I look at mathematical education and I'm like, I'm not sure if this is encouraging people to play. I think play is really deeply necessary for finding new mathematical structure, and I encourage anyone to do it. Let's stop this because I want to see if this ever sorts itself out. Oh look, there's another aliasing line. So it has kind of sorted itself out into grids now on this scale. These lines are... This one looks like it's, 45 degrees. This one looks like it's half that. Maybe 30 degrees. Let's finish the video.
Just like our friends the Woodlocks. You might be looking at a portrait of one of your ancestors, which is absolutely astounding if you ask me.
Also, something I was saying is kind of terrifying, but it is sufficient for that to only happen once. Rules of probability suggest that if it happens once, it will probably happen quite a few times. And we may be the combination of different RNAs coming from different places. Not each human. We all share some quite common ancestry. But this is for another time. I'll say talk about cultural evolution for another time. Let's just finish the
In the
video.
next video, we'll continue adding to our model, and we'll break the news to this orange blob that exponential growth can't go on forever. See you then.
So I hope you enjoyed that. I'm gonna go cook some lunch. Tune in tomorrow for another midday book club. Oh, I'm gonna look at this link that Alexa just sent. If I actually click on the replicator and it should work. Oh yeah. Oh, and this is in Live Viewer. So, I want to randomize the graph. What does layers do? Does any of this do? I think that will also randomize the rules. No, that's just a grower. Whereas some of them, it became stationary, the interior. Here, clearly, oh, look at that. So that is an example of a stable-ish structure that has developed out of the noise. Like, the same is happening there. Is it happening down here? No, it's just these ones. One second. '96 period replicator. So this is just replicating over a much longer time scale. Interesting. Is this... Oh, it's specifically a Game of Life wiki. I reckon we'll be returning to this in future book clubs. Thanks so much for joining. I will be back. Might be back after lunch. I will certainly be back tomorrow morning. I'm liking this kind of like 2 hours of work a day is not a lot, and I'm doing a little bit more in my own time, but it's not a bad minimum to be holding myself to. So come back, join. When I'm not looking at these, I'm looking at galaxy simulations, and honestly, I'm enjoying this. Like, there's just so much to be looked at in these simulations. And yeah, I'll be back tomorrow. Also, probably be back this evening playing some more Disco Elysium, which so far I'm absolutely loving. Its way of representing thought processes is exactly something that one of those things I didn't know I wanted to see in games, and as soon as I've seen it, I'm like, yes, I want this in every game. And it also basically reads like exactly what the NSA are one day going to bring up against me in court. Like, it's forcing me to make decisions about like how anarcho-socialist I am live on stream, which is terrifying, but also really interesting. So come back at some point this evening for that. Probably. See you later. Have a lovely day.